Good evening, everybody. Thank you very much for coming. Lovely big turnout. Got some nice news, and that is that Professor Nigel Sparrow, who was present 2 years ago, has been awarded OBE in the New Year's Honours List this year. So that's fantastic. So big congratulations to him. Apologies from Dr. Suresh Patel. The minutes of the last meeting on determining the colour of dinosaurs are available outside on the foyer or on the internet, on the website. The talk is also available on iTunes. The Medico-Legal Society is having a talk on the 21st of January at the Rope Walk Chambers, and it's Professor Ben Olivier who's talking. The next social event is a week on Friday, which is the Burns Night on the 23rd of January, and we have a tour of the Castle Rock Brewery on the 25th of February. I'm delighted to welcome Professor Jo Haigh, who is tonight's speaker. Jo is Professor of Atmospheric Physics at Imperial College London. She's also co-director of the Grantham Institute for Climate Change and the Environment, and also the lead author on the third assessment report of the Intergovernmental Panel on Climate Change. I was telling that Nigel Sparrow got an OBE, but Jo Haigh in 2013 was awarded a CBE. Not only that, she was also elected a Fellow of the Royal Society, so congratulations. So Nottingham has been blessed with rather less severe weather than a lot of other parts of the country, so it's great that no one had any problems getting here to hear about Jo talking about climate change. So, Jo.
Well, thank you for that very kind introduction and for the invitation to come and speak here. I think the title I gave originally was Solar Variability in Climate Change, but I thought I'd talk about climate change more generally in the context of what is understood and perhaps some of the misconceptions that people have about it. And I'll also put a little bit in there about the sun as well. So why do we bother with this? Well, one reason is that we need to sort of know what's happening in the climate, and there is some strange representations in the media sometimes. So this is a little while ago. Global warming, it's natural, say experts. And this was a report that was compiled by someone that got together all the papers they could find that had been published on the topic of climate and the sun, and assumed that everybody who'd written on that topic assumed that the sun caused all climate change. So my name was on that list. So it was completely, disreputable. But there we are. It's evidence in the Daily Mail. Here's another one. Some of you may remember this programme. It was a while ago now, The Great Global Warming Swindle. And the swindle was being pulled on the great British public by climate scientists in persuading them that it was greenhouse gases that were causing climate change, when in fact it was all down to the sun. Lovely programme, beautiful graphics, really nice to watch. The science was complete rubbish, but there we are. Now, this is Boris Johnson, Mayor of London. Something is up with our winter weather. He noticed it was cold a winter or so ago. Could it be that the sun is having a slow patch? Now, I don't know where he's got this information from, but, it's clearly of interest. Nigel Lawson goes one stage further. It's mumbo-jumbo, says Nigel Lawson. It's economic nonsense and morally outrageous. We're getting a bit, close to the bone now. We have The Guardian, obviously, having a slightly different perspective. This is now quoting Nick Stern. Part of an international pattern and demonstrates urgent need to cut carbon emissions. You can see there's a whole range of things here. And as climate scientists, what we have to try and do is understand the science, say what we do know, say what we don't know, and say, uncertainty ranges on all these things. So it's quite a difficult position to be in, but we do our best. So I'm going to talk a little bit about, I hope you won't find this at all patronising, but just to sort of put it in context a bit about the science of climate. So clearly not to scale. We have the sun and the earth, and the sun's radiation is coming and warming up the Earth, and the Earth gets warm and gives out heat. And if you know how much radiation is coming from the sun, which we do, you can work out what the temperature of the Earth should be in order to give out the same amount of radiation to have a nice balance. And if you do that calculation, you get that the temperature of the Earth is minus 18 Celsius. Now, something wrong with that. Clearly, the surface temperature of the Earth is not, on average, minus 18 degrees Celsius. So why is that? Well, the reason is the greenhouse effect. So let's have a look at this slightly complicated picture. But what we've got here is here's the solar radiation coming in from the sun, and here's the heat radiation going out from the Earth. But you've got all sorts of things messing around in the atmosphere down here, and in particular, we've got greenhouse gases, and you can see this is the heat radiation being trapped. So I'm going to show that again in a slightly more simplistic graphic, and you've got to forgive me for my sort of not very sophisticated graphic skills, but never mind, here we are. So here's the sun, here's the radiation coming down, some of it's getting to the surface, some of it's escaping to space. And about half of it gets through the Earth and gets absorbed by the surface. So the surface warms and emits heat radiation, and then the atmosphere is sitting there, and that absorbs 94% of this heat radiation. And that's, of course, composed of molecules which get hot, but they radiate it all out in different directions, including downwards. So that further warms the surface. And this is the greenhouse effect. It's not how garden greenhouses work, but that's just the label it's got. And so you can see that it's entirely as a result of the fact that the atmosphere lets through solar radiation, but it doesn't let through heat radiation. And this is very fundamental physics. It's been known about since Fourier, I think, first had this idea. And certainly back in the 19th century, people were talking about how this is warming the atmosphere. So it's very well understood physics. So now we need to think about what it is in the atmosphere that's doing this absorbing. And there's a number of greenhouse gases. This picture here is a spectrum in the infrared, so it's wavelengths from 5 microns here up to 70 microns there. And we've got some curves here. The red one is the radiation that would be leaving the atmosphere if it was just all a uniform 21 degrees Celsius and no greenhouse gases. The one with the blue colour is a measured spectrum of the radiation leaving the top of the atmosphere. And you can see it's got a shape that's quite different from this red one. In some places it's rather similar. So here, the radiation getting out is at temperature of 21 degrees C, which is something like the Earth's surface temperature. So what that's saying is at those wavelengths, the radiation from the surface can get to space. But many other wavelengths, you see, that's not the case. And in particular, there's big chunks out of this spectrum here, and these are labelled with particular gases. And the ones that are doing the most is water vapour here, and water vapour here, and ozone, and carbon dioxide with this bite out of here, which is near the peak of this spectrum. So, an important thing to note is that the main constituents of the atmosphere, which of course are nitrogen and oxygen, have no effect at all at these wavelengths. So they're not doing anything. They're sitting in the atmosphere, but the radiation can go straight through, and they won't notice. So we've noticed water vapour. We've also noticed carbon dioxide. So what about carbon dioxide in the atmosphere? Sorry, this is a slightly faint picture. But what I'm going to show you now is various measures of the carbon dioxide concentration in the atmosphere. So we've got time along the bottom axis and concentrations up the top, and the units of parts per million. So this is the most recent data. You can see about 5 years worth. And there's an annual cycle. This is taken from the top of a mountain in Hawaii, so the air is very clean. And the annual cycle is because of the plants growing in the northern hemisphere and absorbing the carbon dioxide in northern hemisphere summer, and then giving it out again in the winter time. So there's an annual cycle you can see here. but you also see a trend from lower to higher values. This is a similar thing, but now going back 50 years, and here's the little annual cycles, and here's the upward trend. Going from 320 to, it actually reached 400 parts per million recently. So I'm now going to show you records of carbon dioxide going back longer periods. This plot here has got exactly the same data as that, but it's got an axis which goes down to lower values. And most of the other plots I'm going to show you have all got the same vertical axis, but they're going back further in time. So this is the same as that going back to 1960. This one's going back to about the year 1000 or so. And that little red bit there is this red bit here. And you can see it's sort of flattened off at about sort of 290 or something parts per million, all the way back to past the year 1000. Now we're going back 5,000 years, 10,000 years, and this is all from ice cores measurements. And you can see it's sort of fairly flat at this 260, 280 value. Here's some more. This one is going back hundreds of thousands of years. And you see it going padoink, 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 padoink. These are actually ice ages. I'll come back to that in a minute. But this vertical axis is the same. So it's not going any higher than it has been recently here. This one is millions of years, 5 million years, 10 million years. And again, it's got the same vertical axis. And you've got to go back to at least several million years in the past. This is a completely different axis now. You see it's thousands of parts per million before you get very high values of carbon dioxide. So to put that in context, first primates appeared on Earth then, first Homo species then, and modern humans appeared then. So in terms of life on Earth as we know it, hasn't existed with anything like carbon dioxide levels anything higher than sort of 300 or 300 or so parts per million until recently. So we are in a new world. And the carbon dioxide is unremittingly going up. We know it's not natural because we can do isotopic analysis of it, and you carbon date the carbon, and it's come from old sources. It's come from oil and coal. So we know quite clearly that this is from burning of coal and oil. But you might say, well, 400 parts per million, what? 4 molecules in every 10,000. Why would that have any effect? So we go back to this spectrum again, and I note this bite here. And we're also going to look at some of these other gases. So the next picture I'm going to show you is actually the difference between if there was that gas not there and the gas being there. And the different colours represent different gases. So this is the same spectrum again. And you can see the water vapour is having most effect at the sort of two edges, over here and over here. And if you add up that whole effect, you get these units of minus 70 watts per square metre. That's saying that the fact that the water vapour is there is making there be less, 70.6 watts per square metre less energy getting out to space than there would be were the water vapour not there. I hope I said that right. And then we have carbon dioxide next. And you can see there's this big bit here. So the interesting thing about carbon dioxide is that it's not as strong a greenhouse gas as water vapour, but it just happens to be where water vapour isn't absorbing. That's just a sort of luck of the draw with the molecules and how they behave. So it's where there's no water vapour, and it's also, you'll note, near the top of this spectrum. So most of the radiation would be going from this wavelength region, which just happens to be where the carbon dioxide is absorbing. So it's having a particularly large effect for those reasons. And then you see there's some other gases, ozone and methane and things are doing a bit as well. So the reason that carbon dioxide can have an effect is that there's little absorption by other gases in the same region as it's absorbing, and it's near the peak of the infrared absorption. So it's sitting there doing it at these particular wavelengths are going to be most effective. So you will hear people, sort of climate skeptic types saying, well, it's only a few molecules, how can it have an effect? But the physics is quite well established. So that's that picture again. And so what we've got in this picture is, this is the greenhouse effect now, and you can see this trapping of the heat radiation where it's coming from the surface, it's getting absorbed, and then a lot of it's coming back down again. Only a smidgen of it actually gets directly to space. But the amount that gets to space to balance the incoming solar radiation is mainly coming from higher up in the atmosphere, which is colder. So that's doing the balance that we need for an equilibrium situation. And here's the sun's radiation coming in. Some of that gets reflected back to space, and some of it gets reflected at the surface, and this is absorbed. So the point to be made is that changing any stream on that picture will affect surface temperature. So I've been talking about greenhouse gases, but if you change something that reflected solar radiation, either down here or up there, or if you did something that changed the absorption of solar radiation in the atmosphere, any of those would affect the climate. So you may have heard people talking about geoengineering, which is where humans say, okay, we've been affecting the climate, we're warming it by increasing greenhouse gases, we will now compensate by doing something else. And there's some varying degrees of madness. I mean, some are not so bad, but the maddest one is where you put great big mirrors in space. The idea is to reflect more solar radiation to space, less of it gets to the surface, you cool the climate, compensating for the greenhouse gases. I mean, that's just one idea, but it's just an excuse not to cut the carbon emissions, really, and it's also various engineers think it would be fun to try. So I'm going to talk a bit about the sun, but first I'm going to talk about power and energy usage. So the average use of energy in the UK per person is about 4 kilowatts. Total human power consumption is about 15 million or 15 English billions watts. And currently 86% of that is coming from oil, coal and gas. The world's largest nuclear reactor is 8,000 million watts. And the Three Gorges Dam, which is just about finished being constructed in China, hydroelectric plant, is, I'm losing the plot with all these zeros, so I'm going to define a new unit. My unit is 1 HPP, a huge power plant. So that's that one. That one's about 0.4 of an HPP, and we need 670 HPPs. So unless the 670 countries want to build huge, gigantic hydroelectric stations, I don't think that's going to happen, but that's what we need. So what about the sun? What about solar energy? The solar power absorbed by the Earth, this isn't the solar power being emitted, this is the solar power being absorbed by the Earth, is about 5 million HPP. So you'd think, well, let's have some solar energy. It's pretty obvious. I'm being slightly disingenuous, of course, because much of that energy is used in all sorts of other ways. But you can see it, just getting a little bit of it to do what we need, rather than burning fuel, oil and carbon-heavy fuels, seems so obvious. And it's lucky that there's a lot of new technology in photovoltaics and other clever ways of extracting energy from solar energy, and I do hope that's going to produce, probably not fast enough, but some of the energy that we need. So that was the point I was going to make. And then I was going to talk a little bit about the sun and climate change. So the amount of solar energy coming in is obviously huge. And we talked right at the beginning about the global warming swindle, and it was all the sun that is to blame in terms of causing climate change. So it's not a stupid thing to suggest. I mean, if the sun's changing and it's so responsible for the energy that's coming into the atmosphere, perhaps it could be causing climate change. So let's consider that. First, we're going to think about how solar energy might be affected. So here's the Sun, here's the Earth's orbit around the Sun, and the orbit is defined by 3 different parameters. So first of all, we have the eccentricity of the orbit, so it's not circular, it's elliptical, and there's a measure of that, and it varies on a timescale of about 100,000 years. There's another parameter which is the tilt, so that is the axis of the Earth isn't pointing perpendicular to its plane of its orbit, it's slightly pointing into the centre, and that's varying on a timescale of about 40,000 years. And the last one is the precession of the orbit, so that's telling us the date around the year at which the North Pole is pointing in towards the Sun. So it might be at that far end, or it might be, this point here, so that's another parameter, and that's varying on about 20,000 years. So on these very long timescales, you can see there's scope for changes in the solar energy reaching the Earth. And that's not going to affect just sort of the total amount, it's also going to affect where it falls on the Earth. So you can see this is a plot of, this is just 1 year now, but it's showing you, as a function of latitude, the amount of radiation that's coming in at the top of the atmosphere. And I love this plot. It's got so much information in. Obviously, the red's more radiation and the blue's less. So we've got summer in the southern hemisphere, summer in the northern hemisphere. We've got winter. So at the polar night, there's no radiation coming in at all. In the summer, you'll see that there's more in the southern hemisphere summer than the northern hemisphere summer, and that's because the elliptical orbit, it just so happens that in January, the Earth is closer to the Sun than it is in July. So the axis is, the North Pole's pointing towards the Sun here, and the South Pole's pointing towards the Sun here at that point on the elliptical orbit. You'll also see that the most radiation is actually at the pole. This is daily average in summer, not at the equator, which perhaps is not, you wouldn't have thought is immediately obvious. So, I just like that picture. But I really put it up because what it shows is that you've got a very strong seasonal variation at high latitudes. And I'm going to use that information in just a minute in talking about ice ages. So this is the temperature from the Vostok ice core in hundreds of thousands of years. And it's going whoopity, whoopity, whoopity. And you may remember that shape because I showed you it essentially already in terms of carbon dioxide. So these are ice ages. This is the interglacials, and here's the ice ages. And what we think is happening here, it's being influenced by the eccentricity of the orbit. If you remember, that's varying on timescales of 100,000 years. But of course, if that was the only thing that was happening, this would be quite smooth because the orbits are not changing suddenly. They're very smoothly changing. And it's not. It goes up very sharply, and then it sort of has a slow decline again, and up very sharply, and has a slow decline again. And we think what's happening is that the sun causes the initial warming, but then carbon dioxide in natural stores, for example, in the oceans and in clathrates and in sediments, gets released. And so you get more carbon dioxide, so you get more warming, so you get more carbon dioxide, it's a positive feedback, and so you get this very sharp increase. So some of the climate skeptics use this plot to say, oh, well, we've had it all before. We've had carbon dioxide varying with temperature. This isn't human-induced, so we don't need to worry. I'm afraid it's quite the opposite. It's not at all reassuring, because what it's saying is that whatever is causing the initial warming, you will get a positive feedback from carbon dioxide in natural reservoirs. So you can't, this is perfectly natural, but it's a feedback effect. It's not a forcing effect. Then I just wanted to say a little bit about the reasons why you get ice ages like this, and it's related to that previous picture I showed you with the seasonal insolation. And it's happening when you've got a particularly strong tilt. So if you get a particular build-up of ice during the winter at the pole such that it doesn't have time to melt during the summer, and then it's reflecting the solar radiation back to space, so preventing some of that getting into the Earth, then you get a build-up of ice and you get an ice age. So it's a slightly complicated combination of these different factors. But yeah, that's the story. So this is essentially due to the sun and reinforced by natural carbon dioxide. But that's not to do with changes in the sun, that's just due to changes in the Earth's orbit around the sun. So you might like to think about whether changes in the sun are going to affect the climate. So do we know that the sun changes? Well, since ancient times, people have observed sunspots and known that the number of spots on the sun is varying. This is a picture of quite a spotty sun, and there's a sort of quasi 11-year cycle in sunspots, and this is going back over the last few solar cycles. We've got data like this going back in the Paris Observatory to at least 1600, so we know that there's been this sort of cycle right the way through. But you'll notice that the solar cycles are not all the same length and they're not all the same amplitude, so they're quite variable. But it's a very well observed phenomenon. So that particular picture of the sun was taken when the sun was quite active. It's 2001. And then there's a solar minimum here. And if you can notice, this solar minimum is quite low. And it's also quite long. And the sun had no spots for quite a long time. We were just thinking, when's it going to get active again? When's it going to get active again? And it did. And you can see it's come up again now, but we're in a really wimpy solar maximum. This is a picture of what the sun was doing this morning. I downloaded this picture, and you can see, compared with that solar maximum, it's really not very impressive. So sort of going off at a tangent slightly, there's quite an interesting question. The solar physicists are considering whether the sun is now heading off towards another sort of minimum behaviour, and so we're interested in what that might mean for climate. But it's all very well talking about sunspots, but how can sunspots affect the climate? I mean, they're just little black spots on the surface of the sun. So we've got measurements from satellites back to 1978 of solar radiance, actually the amount of energy coming out of the sun. So here we are in watts per square metre. And these coloured plots here are all different satellite instruments, composited, so you get a sort of record. And you can see that they are agreeing that there's an 11-year cycle in the irradiance coming out of the sun. And this is the sunspot numbers for comparison. So when it's more spotty, you get more radiation. It's only about 0.1%, or 1 and a bit watts per square metre. But it is happening. So if you're concentrating, you remember that the carbon dioxide trapping is something like I've forgotten what the number is myself now. Something like 20 or 25 watts per square metre. So you can see that these are the sort of numbers that are non-negligible. So just to go off at a slight explanatory loop, when people first started trying to measure radiation from the sun, and they had radiometers that sat on the ground, and they put them up high mountains in the west of the United States where they thought the air was clear and they'd be able to measure it properly. They thought that the sun would have less radiation when it was spotty than when it was not spotty, for the perfectly reasonable suggestion that if it's got black spots on, there would be less radiation coming out. But we know now that's not the case. And it's not the case because this is a picture of a sun in the ultraviolet. And you can see that there's these little black spots, but associated with the black spots, which you can't see with the naked eye. Well, you wouldn't want to look at the sun with the naked eye. I tell doctors these things, sorry. Anyway, there's these bright patches which are called faculae. And in fact, the faculae go with the sunspots, and they more than compensate. So when the sun's got more spots, it's also got more faculae, and they win out, giving you the net additional radiation. So that's Yes, so I included that because we've only got the satellite measurements going back to 1978. If we wanted to know what the radiation was in the past, so we might think about what past climate was doing, we haven't got satellite measurements, and as I said, the people at the surface couldn't measure these sort of tenth of a percent accuracy, and they weren't getting any consistent relationship with the sunspot cycle at all. So it's not possible to do it from the Earth's surface. So if you want to go back in time, you have to use some sort of empirical relationships between these sunspot records, which we have got going back, and what we know about the radiation relationship to sunspots. So this is an attempt to do this. This is somebody's reconstruction of what the irradiance would have been in the past. And you can see we've got these 11-year cycles in radiation. And you go back to the late 17th century, and there's something called the Maunder minimum in sunspots, where there weren't any sunspots observed. And it wasn't just because nobody was looking. They were looking. They knew that they were there. They'd observed them in the past, and they were trying quite hard. But there's records of people writing no sunspots again for quite a long time. And so this is called a grand minimum in solar activity. And it's been observed that that is coincidental with something that has been referred to as the Little Ice Age, or when there was quite cold, at least in Western Europe. And so what effect does this have on climate? So I'm going to put that question there. I'm going to move away from it and come back to it later in the talk. What I'm going to talk about now is computer models, because much of what we do in terms of analysis and understanding climate nowadays is using computer models. And you can use them for understanding the physics, but also for forecasting. And it's the same models that are used for forecasting the weather as are used for forecasting climate or understanding climate. So we'll just look at that. Now, what I'm going to do now is something that you're never meant to do in talks to a general audience, and that's put equations. Now, I'm not putting equations to try and make myself look clever or anything like that. It's a specific reason, which I hope you will appreciate when I've done it all, to show you that there's fundamental physics in these computer models, and just to give you an idea about how the models work. So, laws of physics, Newton's second law, I won't test you, force is mass times acceleration. And what are the forces acting on the air? Gravity, pressure gradient. So you know on the weather maps you get pressure gradients, and if it's high pressure over there and low pressure over there, there will be a force trying to push the air that way. Earth's rotation has an effect, and there's be frictional effects. And we can write down that horrible, I know it looks horrible, but you know, there is a reason. I'm not trying to be clever. There's a reason for me putting that up there. I'm going to come back to it. That's one equation. Conservation of mass. What goes in must come out or get squashed. So that's the density that's getting squashed. That's the going in and coming out. First law of thermodynamics, which is just conservation of energy, really. If heat is added, the air will get hot or it'll expand. So here's an equation that says that. This is the heating going in. This is a change in temperature, and that's the expansion. Ideal gas law, you'll remember PV's RT from school. That's another way of writing it. So that's really, really fundamental physics written down in equations. And if I write these, this is why I put them here. Here's the four equations again. And what I've done now is I've colour-coded the variables. So what we've got is pressure, density, temperature, and wind. There's three winds because it goes in three directions. And we've got 6 equations in 6 unknowns. It's simultaneous equations. You know if you've got that, you can solve it. So these are the equations. You don't need to understand the details, but you can understand that we've got 6 equations in 6 unknowns. So it's a solvable problem with a slight caveat, which is not very slight, but I mean it's, you know, in this context, the caveat is if we know F and Q. The F is the friction, and the Q is the radiative heating. But this is the fundamental basis of all weather and climate forecasting models. So you write down the equations in a sort of digital form, and you solve them for these variables, and you step in time, and you see what happens next. And you can step in time in minutes, or you can step in time in years. You put them on a three-dimensional grid. So here's a typical grid that you might use for doing these sorts of models. Oh, and this is just an example. That looks a bit blurry. So the European Centre for Medium-Range Weather Forecasts, which is in Reading, is one of the best weather forecasting, if not the best weather forecasting service in the world for medium-range forecasts. And so they're thinking this morning, but you can't really see the numbers of what the temperature is going to be in 9 days' time. And this is their forecast for what sea surface temperatures are going to do in 3 to 6 months. So that's just using one of these models to do that sort of analysis. This is an El Nino, in case you're interested. So that's what the models are doing. And you might be going, all sounds a bit easy. It all sounds fine. So why aren't weather forecasts perfect? I've just made it all sound so easy. I'm afraid it's the F and the Q. There's complications. I mean, look, there's the real atmosphere. It's not really quite grid box and all the rest of it. So the first thing is the grid size. And you'll hear that the Met Office is increasingly wanting, more and more powerful computers. And one of the reasons, or the main reason that they want more and more powerful computers, is so that they can get the grid size smaller and smaller and smaller and resolve better and better the features, both horizontally and up the atmosphere. You don't need to look at all these pictures. It's just to make the point that there's all sorts of horrible physics going on in clouds and things that weren't in my equations because they were all carefully hidden in that Q thing. And so that's a lot of complex processes that we need to include. And then another important thing is initialization. So if you're time stepping a model, you've got to start from somewhere. Now, if you're at the Met Office, you've got today's forecast. You can use it for tomorrow and you can use it for the next day. But all the time they're absorbing extra data. So it's a sort of constraining effect. They're getting real measurements rather than what their model's telling them. So you've got the measurements from satellites, you've got measurements from balloons and from aircraft, and it's all being absorbed into the model every 6 hours when they run it. And so you need to initialize the model from somewhere. You do that for weather forecasting, you also do it for climate studies. And so one result of initialization, you may remember, some of you may remember, the great storm of October 1987. That was Kent, the trees all blown down and various people got badly, and this ferry got washed up. That wasn't forecast by the British Met Office, it was forecast by the French Met Office. And you may remember, if you can remember, the poor BBC weather forecaster, Michael Fish, who said in a sort of slightly patronising way, "Oh, some woman's phoned up from Guernsey saying there's a hurricane on the way. Don't worry, dear, there isn't." And that's because she'd heard the French weather forecast, so she knew what they were forecasting. And the Brits hadn't got it because they hadn't properly initialised their model, or they'd missed some data that was available from the Atlantic, and the French had used it and they hadn't. And if they'd put that data into their model, they would have got the forecast much better. So that's just showing you the importance of initialisation and having real data to get into the forecasts all the time, not just computers. Right. Another point is some people find it a bit worrying that, the weather forecasts are not perfect. So how can we possibly say what the climate's going to be in 100 years if we can't do it properly in 10 days? The point is that we're looking at slightly different things. With the weather, we're looking at, what it's going to be in Nottingham or London or something over that sort of region, specifically on a particular day in the future. With climate, we're not doing that. We're saying, what might it be in central England, typically in January 2050 or something? So you're not doing a precise forecast. You're doing it's a sort of typical value that it might be. And importantly, what you're also putting on those predictions is a spread of uncertainty or a range of values. So the forecasters like the European Centre, they will do what's called ensembles of model runs. They'll start with slightly different initializations, and the models will track off in their own way, and then all give slightly different answers. So you get a spread around what the prediction is. Right. Right, on to climate change. I think I'll get there in the end. So what do we want to do? So this is a temperature time series. This is going back, that's the year 400 there. Sorry you can't really see this, but this is temperature anomaly relative to some value. And all these different coloured curves are different people's estimates of what the temperature was doing over that time, based on things like tree ring records and ice cores and all sorts of other sources. And you can see they're quite variable. But there's a general sort of warming there and cooling there. And then this little bit at the end, the black curve there, is actually since we have instrumental records, so since about 1850 or so, there's real thermometers and things that are measuring temperatures rather than these indirect indicators of what the temperature was doing. And it's this extremely sharp warming that's been going on over the last sort of at least 50 years that's known as global warming, and is what we're trying to understand. So we can do that in various ways. What this is doing is running some of these climate models and looking at different forcing factors. So all the grey wiggles on here are equivalent to the coloured curves in the previous plot. So they're different people's estimates of what the temperature was doing over this 600-year period. And the coloured curves are computer model simulations with different forcings in. So we've got the one with the greenhouse gases in, which is the red curve, and that's coming along here, and then it's going shooting up here because we know what the carbon dioxide has been doing. We saw that the carbon dioxide is increasing, and it's causing this warming. But there's other factors in there. There's the effect of volcanoes. Now, when volcanoes do big eruptions, they chuck a load of stuff up into the atmosphere, and it reflects radiation back to space, and that cools the climate. And there's clear indications of that in various spiky temperatures, and that's it, more recently since there was an eruption of Mount Pinatubo quite recently, and there was a clear dip into global temperature following that, so that's well observed. There's changes in this green here is labelled aerosol. So along with increasing carbon dioxide and other greenhouse gases, urbanisation has led to increase in emission of particulates, and in particular sulfates, or sulfuric acid, sulfur dioxide, which turns into sulfates and sulfuric acid droplets. And they hang around as little droplets in the atmosphere, and they behave rather like the volcanoes do. They reflect the sunshine back to space. So this dirty air has actually been cooling the climate. So it's a sort of rather unfortunate consequence of cleaning the air, is it's going to add to global warming. Then there's some other curves in there. One is changes in land use. So if you, for example, deforest and you take out the dark forests and you replace it with bright vegetated, wheat fields or something, then that will get brighter, so it'll reflect more solar radiation to space, so you get a slight cooling effect. Curves labelled solar, two different blue curves, and they are different people's estimates of what the sun was doing. So I showed you that one with all those wiggles and the Maunder minimum. These two curves both have a Maunder minimum and variations, but the light blue one has much more extreme variations than the dark blue one. And I think there's two interesting points you can see from this graph. One is here. This is so these are labelled. These are solar minima. The effect of the sun, whichever one you take, but even if you take the more extreme one, actually was quite small during the Maunder minimum, and it's the volcanoes that probably caused that cooling. Even if the cooling were global, which it is. It's not very strongly global. It was quite cold in Western Europe, but it wasn't particularly cold across the globe. So the whole thing about the little ice age and the sun is probably not very strong. So that's the one thing, that the volcanic impacts are probably more significant than the solar. I mean, they're both natural. You can't do much about either of them, but that's an observation. And the other thing is that whichever solar curve you use, I mean, this dark blue one's doing almost nothing, but the light blue one is sort of flattening off here. You can't get global warming due to solar activity, not using anything we know about the sun. So it's not that. Was looking back at those sort of proxy temperature records. If we now focus on the period which has got instrumental measurements, so these are actually the thermometers and things across the globe. There's two plots here. They both got the same black curves, which is the observational record, but they've got different coloured curves, which are the model simulations. And this one's got only natural forcing, so it's got the volcanoes and the sun. And you can see the colours wobbling along here and going off here. This one's got all the forcings, which means all the other things I mentioned in the previous slide as well. And there's a much better match between the coloured curve and the black curve when you put all the forcings in. The other reason I wanted to include this plot was because of all these little wiggles. So I've mentioned about the problem of initialisation. We have to start the climate models off somewhere with some sort of data, and it won't be precise, it can't be precisely accurate. So what we do is we run ensembles of runs where they each start off from a slightly different starting point and see which way it evolves. And each of these individual lines is another simulation. So you can see they give a broad spread of values around this mean of over here it's global warming and over here it's not. So there's an important point about this is that the Earth isn't an average. The Earth is one particular realisation. It is itself. We just don't happen to know which one of those wiggly curves it's on, or indeed it may not be any of them. It might be on another one that's not on that plot. So if you can't actually say that it's not going up here and down there, we can't say that. What we can say is that on average, over the next, if we predict this into the future, decades, it will sort of on average do something like this within a spread. So it's one of these wiggles, but we don't know which one it is. You may also have heard perhaps about the hiatus or the pause in global warming. There's been some talk about that. This is to do with, this is again a temperature record, and it sort of looks like it's been flattening off. There's a lot of fuss about that. Oh, global warming's gone away. We don't have to worry about it after all. If only that were true. I'm afraid it's very unlikely to be the case. You can see there's been all sorts of noise in this record. It's a natural system. It's not going to be all smoothly varying. In addition to which, the people who say the hiatus usually start in 1998 here, which is when there was a very big El Nino, which is warming the tropical sea surface. So that's natural warming of the surface. So it's sort of flattened off a bit, but I don't think we can assume it's not going to sort of start going up again. In addition to which, there are many other indicators that climate change is continuing. Here's some of them. Sea level change here is trucking on up. There's no hiatus in that. This is the upper ocean heat content is coming up, so it's going up. Sea ice is going down. Snow cover is more difficult. There's no obvious real trends in there, but it's certainly not going up. So there's all sorts of interesting discussions about if there's a hiatus and if so, why it's there. But whatever, these other indicators are saying that climate change is happening. So I must not go on too much longer. Regional variation, so it's not equal warming everywhere all the time. That's another sort of misconception, perhaps, that global warming means every place on the globe warms all the time equally. It's not. There's, especially over land areas, warming more than over the sea. That's observations. Okay, so this is to do with how you project into the future. So, I've talked about the uncertainties with models, but you've also got to predict the economy or predict the CO2 to know what you're using as a base for a forecast. So, of course, there's different assumptions you can make. And these are different assumptions on CO2 emissions based on different assumptions about what people do to stop emitting in these cases, or not stop emitting, which is that case. So that's emissions, but of course emissions don't map immediately onto concentrations because the carbon dioxide can last in the atmosphere quite a long time. And you can see here, even if you stop the emissions pretty quickly, it only just flattens off here. This one, you're turning the emissions around quite sharply, but you're just flattening it off into the future. There's a very sort of long time scale on this, and if you do this business as usual scenario, it just shoots up. So these are predicted global surface temperatures based on the least bad and the worst of those predictions. So you can see there's a sort of spread in predictions. This one's about 0.5 degree, and this one's going up to sort of 3 degrees by 2100. This is talking about predictions of precipitation, but they're much more difficult, so I think I'll probably dismiss that one because I'm running out of time anyway. That's predictions in sea level rise. See big uncertainties, but it's going on up. This is an important one. This is much longer timescales. You see, this is 100 years here, and here's 1,000 years. And the point here is that there's a very long timescale of carbon dioxide in the atmosphere. So if we were to peak emissions within the next century, say over here, and then really bring them down, so this is the emissions again, the concentration in the atmosphere stabilises after, say, 100 to 300 years here. The temperature stabilises a bit later, but sea level rise carries on going for ages because it's taking a long time to mix the heat into the oceans. So, you know, the sooner we act, the better. Here's the message from that. That's a complicated one, I'm going to skip that. So I want to end on a sort of perhaps a hopefully more positive note. You'll be aware there's a big conference coming up, the United Nations Framework Convention on Climate Change, Conference of Parties. The meeting coming up in Paris in December. It's called COP21. And all the countries are going to get together and try and agree perhaps on CO2 emissions. So we've had various politicians already making comments. We had Ed Davey in New York basically saying a 40% reduction in CO2 emissions by that date would not be enough if we're going to try and keep global warming to less than 2 degrees. If the rest of the world is prepared to act, the UK is arguing the EU should be even more ambitious. And of course we have got the EU is really leading the world in these things. But that's, you know, positive from the government. But I thought this was even more positive. This is the Foreign Secretary with John Kerry in Boston. And okay, they were at a wind turbine factory, so, you know, had to say something good about renewable energy, but, you know, they don't have to say this. Countering the threat is a true win-win situation for the environment and the economy. And if we could look at it like that and think, you know, we can invest, we can get lots of new technology, we can have wonderful new alternative energies, and that's good for the environment, and it's good for the economy with all this new technology coming on board. So I thought that was incredibly positive. And then we got the recent meeting in Lima. That was COP20. They were looking very congratulatory. You know, it wasn't that wonderful. They didn't agree on anything particularly, but they did agree that it was necessary to agree. So, you know, that was a positive thing. So I think I'll leave it there. Thank you.
Privileged to have you talking to the society. And I'm delighted to say that Jo has agreed to answer any questions.
Thank you. On the map, you showed a map of the world showing the different areas we're getting hotter. I noticed that the North Atlantic was the only bit that was cold.
Yes.
And it wasn't replicated in the Southern Hemisphere.
No.
Could you just explain that enough?
I can't explain the physics. exactly, but it's a very interesting phenomenon that. There's various sort of natural variations in the atmosphere. You've probably heard of the El Niño, which is the natural variation in tropical sea surface temperatures. There's also a natural variation called the North Atlantic Oscillation, which is where the pressure patterns over the North Atlantic are doing this. And it leads to particular changes in the weather in Western Europe. So if you've got a strong North Atlantic oscillation, it gives us stronger winds and more northerly storm tracks and more rain. And it seems that climate change can actually affect the way that these natural modes vary. And it could be that you do get certain regions that are cooler because these that's how they're affected. And it's the North Atlantic looks like that might be one of those. Interestingly, well, I think it's interesting also, it seems when you get the sun's, if I haven't talked really about that at all, but the sun's effect on climate, variability, 11-year cycle variability, or even longer term, back to the Maunder minimum, it might be affecting the North Atlantic Oscillation. So it might be producing the cold temperatures in Western Europe, the Little Ice Age so-called, because it's a regional effect due to the North Atlantic Oscillation, nothing really to do with global average temperatures. So it's a real key, a wonderful question, real key point of current research, actually.
I was wondering whether you could comment on the often suggested idea that a 2-degree increase in global warming is safe, but anything beyond that is not safe.
Yeah, I mean it's a slightly strange thing. I think that the Intergovernmental Panel on Climate Change was asked to come up with a sort of figure as a sort of not a target, a threshold above which we don't want to go, and they came up with the 2-degree figure, above which you would get dangerous climate change. But obviously that's silly. I mean, there's no great difference between 1.9 and 2.1. It's just that as you go much further, everything gets even worse. So even you've noticed that there's been more extreme events already. That was the complicated plot I didn't bother to show, but we've had more floods, more heat waves. And so I think it's more the sort of extreme events that are going to affect the way people live. If you're living in Bangladesh and you're getting... actually, there's an interesting point about that. I work in the Grantham Institute for Climate Change, and we were talking to the people in the public health department, and they've noticed that that pregnant ladies in Bangladesh are getting more hypertension. And the reason is they've got salt in the drinking water. And so it's sort of related to changes in the environment. And so there must be things like that happening all over the globe. The regional effects are much stronger than just a sort of global average temperature increase. So I don't think 2 degrees is anything particular. It's just a sort of bad.
My son lives in Virginia. I've just been over Christmas and New Year. Very nice. As you may know, the price of gas that we know is like $4
Yeah.
and now they're $2 a gallon.
Yeah. And it's very cold in Virginia.
Smaller cars,
Yeah.
all the adverts were about bigger cars.
Yeah.
To emission.
Yeah.
So how are you going to get the Americans on board?
I don't know. It's really bad timing. It's very bad timing. I mean, I think the only thing would be, only positive you might get out of it is that it might make countries more willing to do something on a sort of carbon tax. Because if the fuel is cheaper, then paying a bit of tax doesn't come over as quite so bad. That's looking for positives, really. My son's in Pennsylvania. It's very cold there at the moment.
Could I ask Professor Haigh, how much deforestation has affected our climate?
Yes, so that's a good question. So we're talking about carbon dioxide increases in the atmosphere, and about, I've forgotten the actual fraction, but a significant fraction of that was due to deforestation rather than due to coal and oil. Because, of course, when you cut down the trees, you're taking out the carbon sinks. So that's a significant factor, and there's quite a big research activity in looking at the whole carbon cycle, which is more general than just burning CO2. I think that the countries involved, which of course is largely South America and in the tropical Asia, are coming on board in terms of being persuaded that they should sort of slow down on the chopping. So we hope that will help.
In the context of China opening a new coal-fired power station every week and intending to continue to do so for an indefinite period of time, do you think, what effect do you think European cuts in emissions are going to have in the global context?
Yes. So, I mean, the China situation is very interesting because you're right, they are still burning, and they're burning inefficient coal power stations. But they've got a lot of their own people who are now saying we can't stand it anymore because the air pollution is so bad. It's well, you probably know it's probably killing people. So that they are actually doing things. They're talking about. They actually talked to the Americans after was it before or after that Lima meeting, and agreed that they would come to some agreement. I thought that was incredibly positive. So you're right, it's not good that they're, but I think they're now getting into the mindset. And if they could also persuade India and Australia and Canada, we might be getting somewhere.
Methane is bigger on your chart, but we understood that this is a potential devastating gas if it's released from the tundras and that.
Yes. Yes, absolutely. So methane is a strong greenhouse gas. It doesn't have quite the same long lifetime as carbon dioxide, so in that sense it's not as bad, but in actual specific absorption of radiation it's stronger than carbon dioxide. And as you're quite right, as the ice melts and the tundra warms up, you get release of methane from the clathrates, and that enhances global warming. There's been various sort of scary estimates of sort of sudden emissions of methane and what that would do to the climate. I don't really know the answer properly.
Can I have two questions? My first question is, you didn't talk very much about deep ocean currents, and I think that there's thoughts I have. Specifically, are you the view that the melting of the Greenland ice cap will collapse the North Atlantic line?
Yes.
There they'll lead to very cold winters.
Yes.
Very cold. My second question is...
Can I do that one first? So obviously there's an awful lot of heat stored in the oceans, and there's very, very large-scale circulations in the oceans transmitting this heat around. If you talk about the very deep oceans, the timescales involved are thousands of years, so it would have an effect, but really it's beyond anything that we can really consider as affecting human at the moment. The surface, the more shallow oceans are important, and there's quite a bit of discussion with this hiatus business as to what extent the heat is getting into the surface oceans, and that's why it's not coming up as the surface temperature, and whether it's going to come out again. So that's a sort of, and I also showed you a plot of the near surface ocean heat content continuing to go up. So that's important too. I think the day after tomorrow scenario, which is the one you're painting, where the thermohaline circulation collapses, the climate models have been trying, with the coupled oceans, have been trying to simulate that, and they have to put such extreme forcings on. Don't think that's likely. There are buoys across the ocean that are measuring these the currents, and there was a paper published in Nature a couple of years ago about how they thought that the circulation was slowing down, but then that was not proven. So it's a bit of an open question, but I don't think the dreadful scenario that you're painting is very likely.
My second question is, the Earth is very hot inside, and why has nobody seemed to be looking at actually using that as a free and easy source of power?
Well, geothermal energy. The first thing actually on that topic is some people think, well, global warming, it's all heat coming from below. It's not. If you look at measure the heat coming out from, transmitted through the surface of the Earth from the heat below, it's absolutely tiny. It's not doing anything. Geothermal energy, yes, another source of alternative energies. It's people doing research. I guess it's costly, but yeah, it's up to the engineers really.
One question actually, we're talking about sort of global change on a grand scale, but I know there are certain things that can be locally to mitigate the effects of global warming. And I remember reading somewhere actually that certain areas where you have small pockets of woodland, their natural temperature is generally speaking lower because specifically having woodland,
yes.
you get a natural cooling effect.
Yeah.
Do you think there's actually much scope for using small scale changes in certain areas to limit the effects of global warming? And again, slightly second question as well, actually, will there be increasing issues with higher temperatures in cities, where obviously cities generally tend to be much higher? So will the effects of global warming be much greater in the urban areas?
Yes.
Particularly as urban areas get bigger,
yes.
slightly more extreme.
So I think we're coming back to the sort of regional against the global again. Yeah. I mean, if you're just worried about global temperatures, you're probably not going to do much by greening the cities. But in terms of the environment for the people living in the cities, it's hugely beneficial. And there's a whole area now talking about it's called blue-green cities, where you try and get the water and the environment and the plants and everything, making it cooler and more pleasant. So absolutely, yes.
Okay, thank you, Joe. Can I ask Sue to...
Thanks very much, Jeff. Apparently, Jeffrey asked you to come and talk to us after hearing a podcast on iTunes. I'm jolly glad he did. I understand quite a lot more about global warming now than I did before. It's clearly hugely complicated, and I think we only got a little glimpse of what it's about, but I certainly understand a lot more about it. And I'm jolly glad it's people like you who are talking to the politicians about it on our behalf, and I hope they listen to you as intently as we have tonight. Thank you very much.
Well, thank you for your interest.